Hello friends, mom welcome in this video, that is the mix inhibition. Friends, in earlier video on the non-competitive inhibition, we have obtained an expression for a simple linear non-competitive inhibition which was depend on the equilibrium assumption and further assume that the substrate binding and inhibitor binding were completely independent. Let us now consider the situation where the mix inhibition takes place and the second assumption is not made. So a mix inhibition is a type of inhibition in which inhibitor may bind to the enzyme whether or not the enzyme has already bound the substrate but has a greater affinity for one state or the other. So here I have illustrated it by this diagram which indicates that it is very similar to the non-competitive inhibition. Yes, non-competitive inhibition is also a type of a mixed inhibition. So let us consider the situation where the mixed inhibition will take place. There are two processes by which inhibitor may bind to the enzymes. In one case, E plus I gives EI, where the inhibitor constant is considered as K small I, and in other process, ES plus I gives ESI, where the inhibitor constant is considered as K capital I. Therefore, K small I will become equal to concentration of E into concentration of I divided by concentration of EI, and K capital I will become to concentration of ES into concentration of I divided by concentration of ESI. Friends, we also know that concentration of E into concentration of S divided by concentration of ES is equal to Km, and concentration of E0 is equal to concentration of E plus concentration of ES plus concentration of EI plus concentration of ESI. Now if we continue developing equation considering K small I and K capital I are not identical, then we will get concentration of E0 is equal to concentration of E plus concentration of ES plus concentration of E into concentration of I divided by K small I plus concentration of ES into concentration of I divided by K capital I. Now if we take common E from this equation and ES from this equation and this equation, then we will get concentration of E into 1 plus concentration of I divided by K small I plus concentration of ES in bracket 1 plus concentration of I divided by K capital I. Therefore, the concentration of E is equal to concentration of E0 minus concentration of ES into 1 plus concentration of I divided by K capital I divided by 1 plus I K small I. Now if we substitute the value of this E into the equation of Km, then we will get Km is equal to in bracket concentration of E0 minus concentration of ES whole into 1 plus concentration of I divided by K capital I bracket close, this into concentration of S divided by in bracket 1 plus concentration of I divided by K small I bracket close into concentration of ES. Therefore we will get concentration of E0 into concentration of S minus concentration of S into concentration of ES in bracket 1 plus concentration of I divided by K capital I bracket close is equal to Km into concentration of ES in bracket 1 plus concentration of I divided by K small I. After arranging this equation, we will get concentration of ES into in bracket concentration of S again in bracket 1 plus concentration of I divided by K small I bracket close plus Km in bracket 1 plus concentration of I divided by Ki bracket close is equal to concentration of E0 into concentration of ES. So by rearranging this equation we will get concentration of ES is equal to concentration of E0 into concentration of S divided by concentration of S in bracket 1 plus concentration of I divided by K capital I bracket close plus Km in bracket 1 plus concentration of I by K small I. So by continuing solving this equation as we have solved in earlier conditions, then we will get the rate of reaction or V0 is equal to Vmax into concentration of S0 divided by concentration of S0 in bracket 1 plus concentration of I0 divided by K capital I plus Km in bracket 1 plus concentration of I0 divided by K small I. So this equation is very similar to Maclaurin-Menten equation, only the difference is in between these two values. So now divide both numerator and denominator by 1 plus in bracket concentration of I0 divided by K capital I. Then we will get Vmax into concentration of S0 divided by in bracket 1 plus concentration of I0 divided by K capital I whole divided by concentration of S plus Km in bracket 1 plus concentration of I0 divided by K small I divided by 1 plus concentration of I0 divided by K capital I. Thus here V prime max or apparent Vmax is equal to Vmax divided by in bracket 1 plus concentration of I0 divided by K capital I, and K prime m, that is apparent Km, is equal to Km into in bracket 1 plus concentration of I0 divided by K small I bracket close divided by in bracket 1 plus concentration of I0 divided by K capital I bracket close. So here Lineweber equation is become 1 by V0 is equal to K prime m divided by V prime max into 1 divided by concentration of A0 plus 1 by V prime max. And thus the Lineweber plot will be linear. However, in general, Km, Vmax and slope which equals to K prime m divided by V prime max is equal to Km divided by Vmax into 1 plus concentration of I0 divided by K small I. Thus plots at different inhibitor concentration at a fixed A0 will not intersect either axis, nor will the slope be the same, so the pattern will be different from those characteristics of competitive, non-competitive and uncompetitive inhibition, and is given the name mixed inhibition. It must be realized that this describes the overall pattern observed and does not imply that more than one type of inhibitor is present. In the situation where K small I is larger than the K capital I, the plots cross the left of the 1 by V0 axis but above the 1 by S0 axis. This situation has been termed as competitive non-competitive inhibition because the pattern observed lies between those for competitive and non-competitive inhibition. In the situation where K small I is smaller than K capital I, the plot crosses the left of the 1 by V0 axis and below the 1 by S0 axis. This form of mixed inhibition has been termed as non-competitive uncompetitive inhibition because the pattern is intermediate between those for non-competitive and uncompetitive inhibition. In either case, K small I and K capital I can be determined using secondary plots or mixed inhibition. For mixed inhibition, 1 by V prime max is equal to 1 by V max into 1 plus concentration of I0 divided by K capital I, and slope for the inhibition reaction is equal to slope for the uninhibited reaction into 1 plus concentration of I0 divided by Ki. Hence a secondary plot of 1 by V prime max against I0 will be linear, the intercept on the I0 axis giving minus Ki. A graph of slope of primary plot against concentration of I0 will also be linear, the intercept on the I0 axis giving minus Ki, which means that a graph of K prime m against concentration of I0 will not be linear. The equation for V0 derived above is a relatively general one since no assumption were made about the values of K small I and K capital I, and it can be simplified for special case. If ESI cannot be formed, then K capital I is equal to infinity, and the equation becomes that for a competitive inhibition, regardless of whether the substrate and inhibitor bind to the same or different sites. If the complex ESI can occur but not EI, then K small I is equal to infinity, and the equation simplifies to that for uncompetitive inhibition, when K small I is equal to K capital I, the equation reduces to that for a simple linear non-competitive inhibition. Now we will see the example of mixed inhibition. In gluconeogenesis, the enzyme phosphoenol pyruvate carboxygenase, which is located in cytosol, is responsible for converting oxaloacetate into phosphoenol pyruvate or PEP. When GTP is present, this step is exclusive for gluconeogenesis, which occurs under fasting condition due to the body's depletion of glucose. Phosphoenol pyruvate carboxygenase is known to be regulated by genistein. Genistein is an isoflavone that naturally found in a number of plants. It was first proven that genistein inhibits the activity of phosphoenol pyruvate carboxygenase, in which isoflavone resulted in a decrease in the level of blood sugar. A lower blood sugar level means less glucose is in the blood. This occurs in a subject that is fasting. This is because the gluconeogenesis was inhibited, preventing increased production of glucose. The ability of genistein to lower the person's blood sugar level allows it to be referred as an anti-diabetic property. Thank you.